The difference between supersonic flow and hypersonic flow is somewhat arbitrary. In both cases, compressible flow effects can be seen around an object moving at high speed, such as normal and oblique shocks. In hypersonic shocks, however, the temperatures are high enough for molecular species to dissociate and chemical reactions to occur. A flow is generally considered hypersonic above Mach 5 or 5 times the speed of sound. We are interested in understanding the physics and chemistry that occurs in hypersonic flows as it is necessary for the design of hypersonic vehicles. Information such as pressure, temperature, and chemical species concentration help create a picture of the mechanisms involved in those flows. This ultimately helps us predict the behaviors of objects and vehicles operating in these flow regimes. To measure properties inside an incompressible flow, it is possible to physically probe with a pressure gauge or a thermocouple the region of the flow we are interested in to measure pressure and temperature. This task becomes tricky if we try to do the same in a compressible flow, however. If we are interested in taking measurements in the shock front of a hypersonic bow shock, inserting a physical device in the shock layer would create a new shock layer and render the measurement useless. This is why we need to rely on non-invasive measurement techniques, such as optical diagnostics, to get the information we need. As you may remember from your freshman chemistry course, atoms have an electron cloud with an outer shell that can become excited into higher orbitals, or energy states. These excited electrons will, over time, spontaneously decay back to their ground state, and the energy difference is released in the form of a photon. Molecules undergo a very similar process, except they can store energy internally through vibration and rotation modes in addition to having an excitable electronic shell. Like the energy levels available to the electrons, the vibrational and rotational energy levels are discrete and quantized. The electronically excited state represent the widest steps in terms of energy level in the energy configuration of a molecule. Within an electronic energy level, it is possible to fit multiple vibrational energy levels, and within those, to fit multiple rotational energy levels. Each molecular and atomic species has a unique manifold of internal energy levels which can become populated under certain conditions. By populated, we mean that for a given number of molecules, a certain number of those molecules will find themselves at different steps on the energy ladder at any given time, depending on the temperature. Hypersonic shock layers, especially in normal shocks, are very hot, with temperatures reaching well over 10,000 degrees Kelvin. The hotter the gas, the more molecules and atoms present in it can climb these energy steps. Electronic, vibrational, and rotational modes can be populated independently from each other, which allows us to speak of electronic, vibrational, and rotational temperatures as separate quantities. When those temperatures are different, we say the flow is not in thermal equilibrium. This can occur in very rarefied gas conditions when there are not many collisions between molecules. Another condition for thermal non-equilibrium is when there is a sudden change in entropy, such as in a shock front. Given enough collisions between particles, these temperatures will converge to a single value, and the flow will return to thermal equilibrium. This process is called thermal relaxation. Like electronically excited atoms, the excited molecules will eventually decay back to a lower state and emit a photon. Whereas radiative decay in atoms involve only electronic states, radiative decay in molecules involve all internal energy modes. There are rules which dictate what transitions are allowed and which ones are forbidden, called selection rules. By capturing the light emitted during these transitions, it is possible to measure certain properties of the gas layer emitting the photons. The variation in internal energy modes between species means each species has a different light signature, which can help determine what molecules are in the gas layer. Because the energy levels are populated based on temperatures, it is also possible to know the different temperatures of the gas. Using other techniques, it is possible to measure quantities such as pressure as well. This is how emission spectroscopy and emission diagnostics are applied to the study of hypersonic flow.